Okay, and welcome back to BME 2315. In this lecture, we'll be taking a further look at differential equations. So so I showed you the Lorentz equations on the last slide, which is one of the more famous sets of differential equations. On your homework set, we're going to be using another famous set of differential equations called the Fitzhugh-Nagumo action potential model. And this is basically a simplification of the Hodgkin-Huxley model that you may have seen in your physiology class. Basically, it's able to predict oscillating action potentials down a nerve, or how electrical activity would spread throughout a tissue to cause, in this case, a cardiac arrhythmia is being simulated. And these are really just absolutely beautiful spiral waves. One thing to point out here is that the ordinary differential equation, there's only one independent variable, and so that's how it's just predicting in time. But in the partial differential equation, you said those have multiple independent variables. So it's got time, x, and y. So it's got three different independent variables in order to do this. Here's another just really cool animation that we can get this to work of the same Fitzhugh-Nagumo equations. Yeah, so it's really cool how this looks like a very organic type of abstract art. Okay, so we've been talking about how are we going to solve these differential equations, and in the Euler's method, what we found is that if there was a true solution like this, we were going to take, so the arrow is going to guess the slope right here, and so then here is its then is y predicted, and then there's an error, the truncation error in between the two. Okay, and in higher order Runge-Kutta methods, we're going to do a similar approach, except that we're going to do multiple guesses of the slope. And so I'll give you just the briefest kind of look at what would that look like. So if we had a y true, then it might take an example, a initial guess at the slope like this, and then stop, and then take another slope calculation, K2, and then come back to the top and something like this. So I'm just trying to give you an example of that this will take more iterations, because then I'll take this information and this information and then make a combined result that goes somewhere in the middle. And the reason you'd want to do this is, in general, a combined result is going to be kind of closer and more accurate than just individual guesses. Okay, and so that's why these are called predictor-corrector methods. Okay, so let's talk about an actual specific Runge-Kutta method, and that is called the midpoint method. I'll draw this out for you. Okay, so we had a y true. Okay, and so what it's going to do is it's going to start off by taking the slope from the starting point. Supposed to be an arrow. Xi plus 1, and this is at xi plus 1/2, okay? So it's only going to make a prediction up to the halfway point, okay? And then at this point, it's going to calculate a new slope at k2, and then it's going to go back to the start, and then using that slope that it estimated, it's going to use this. So it's going to say that's the predicted yi plus 1. And so to kind of show that more in the equations, we predict the slope. This looks like the Euler method, right? Except that we're only taking a half step. That's why we only took a half step and not a whole step. Okay, so you take the half step. This first was called K1. And then you're going to plug in y of I plus 1/2 into this, and you calculate calc K2. Okay, and then notice that this is taking a full step, so it's going back to the original point and taking a full step, and then calculating yi plus 1. So because it takes these multiple steps in there, it does a better job than Euler's method. Remember, Euler's method had a single step error on the order of h squared, and this is on the order of h cubed, and a cumulative error on the order of h squared. That's an improvement. So let's now take an example of this approach. And we're going to use the same x over y differential equation to kind of drill in how these methods are a little bit different. Okay, so the first thing is to start off with the slope calculation. So okay, I'll write out my work down here. So for I equals 0, we're going to first take the half step, and we're going to say that is 3, because we started with 3, minus 2/3 times 1/2. This is it's 1/2 because we're taking just half a step. It's 2.667. Okay, and let me fill it in above. So we get negative 2/3, 2.667. Okay, and then next for yi, you're going back to the original y location, and we're taking the ratio negative 1.5 over 2.667 times 1 equals 2.4375. Okay, so then kind of filling in the rest of this like this, and this was 2.4375. So a little bit more work than the Euler's method, but it got a closer result. And here you can go back and look at the slides later just to see more of the math or the rest of these numbers to verify your own calculations. Okay, so now let's look at the error that occurs with the midpoint method. And as you can see here, while the Euler's method did pretty poorly, the midpoint method does much better than the Euler's method. So that's showing the benefit of having these multiple guesses at taking a shot at the solution of the differential equation. Okay, so now let's take a look at the fourth order Runge-Kutta method, which is one of the more famous methods for solving differential equations, because it does a really nice job of having a low amount of error. And but unfortunately, it's a little bit more complicated to calculate. So let's draw this out. And go from a xi plus 1/2 xi plus 1. Okay. Okay, so the basic idea here is I'm going to do my best to graphically illustrate, and then we'll kind of go to the math. We're starting at the beginning, and we take an initial slope estimate, and we take that out to halfway, okay? And then we with a slope of k1. So now at this halfway point, we're going to take another slope estimate that we'll call k2. And then we go back to the original takeoff point, and we're going to go with k2 until we hit the midpoint right here, and go to k3, and then go back to the original, and we take a full step here, and then we take a final or fourth slope estimate, k4. Okay, and then we're not gonna rather than using the results from any single one of these trajectories, we use a combination of them. And so that's how this works, is that the overall prediction is a combination of k1, k2, k3, and k4. And so kind of focus on the equations here, that you remember we're going to first calculate k1, and then we're going to calculate k2, where k1 is used in order to calculate k2, and then in k3, sorry about that, in k3 we're going to be using the results from k2, and in k4 we're going to use the results from k3. So let's look at an example of how this works. Okay, so we got okay, so we start out at -2 and -3, and when I first off start calculating by k1, and k1 is f of -2 3 equals negative 2/3. Then K2 equals f of negative 2 plus 1/2 and 3 plus 1/2 times negative 2/3 times 1. Right, and that equals negative 0.5625. Okay, and then K3 is f of negative 2 plus 1/2 and 3 plus 1/2 times the K2. And so that's going to be negative 0.5517. Okay, and then finally, K4 is given by f of negative 2 plus 1, 3 plus 1 times what we had for K3. Equals negative 0.4085. Okay, and then finally, our overall slope is given by 1/6 K1 plus 1/3 K2 plus 1/3 K3 plus 1/6 K4 equals negative 0.5506. Okay, and so then the final step here is we can now finally use that to update our equation. So we get yi plus 1 equals yi plus vh equals 3 plus times 1 equals 2.4495. Okay. All right, so those are all the steps for just going through one iteration of this method. I'll just put that up here. So why is it worth our bother to have such a complicated method? Well, the here and reminder here the numbers if you'd like to more practice getting out more steps. If you remember looking at these error problems, this is showing what happened with Euler's, and now this is showing with Runge-Kutta. It is very, very accurate. So it stays very close to the analytical solution. And remember, the midpoint also appeared to, but if we show the midpoint and the Runge-Kutta side by side, we can zoom in on what's happening around these individual points, and we find that the Runge-Kutta method actually is still kind of more accurate. It's kind of flatter down here than the midpoint method. So the Runge-Kutta method is really quite good. So that's why we teach the computers how to do these methods. Like with the other methods, taking smaller step sizes can really help you. So this is showing that with Runge-Kutta, even when there's like some divergence, that a smaller step size can help you get smaller and smaller. Okay, so to summarize this lecture, we've been looking at more advanced methods for computing differential equations, and the way that they work is that they're predictor-corrector methods. They use slope information from multiple locations to try to estimate a more accurate solution. Increasing the order of Runge-Kutta increases accuracy. So we went from Euler to midpoint to fourth order Runge-Kutta. And we got increasing accuracy each time. But always the error also depends on the step size, h. So if you can take smaller step sizes, there'll be more computation, so it'll go slower, but it'll also be more accurate.